The first reminder is that you have a midterm coming up a week from today. That midterm is going to run from 11 a.m. to 2 p.m. We know that this is a conflict with midterms in a couple of other classes. If you are in that position and you haven't emailed us already, please email us like right now, or at the very least by the end of the day. We are able to make alternate arrangements for those of you who have midterm conflicts. So just let us know if that's an issue. Yeah?
What lecture is it up to?
So this is the midterm is going to cover up to hidden Markov models, which is tomorrow's lecture, but not particle filtering.
So someone gets syllabus usually another hidden Markov model lecture on Monday. Will that one also be covered?
Yes.
Okay.
Yeah. Sorry. Is the one on Monday just particle filtering? Okay, then no. No. Yeah, so content-wise, it's hidden Markov models except for particle filtering, and I guess Monday's lecture is all particle filtering, so stops tomorrow. Other midterm-related questions? Sorry? It's cumulative, so anything that's happened anywhere in the course now, you're responsible for. Yeah. Will the scale be posted? I'm not sure I understand. I mean, it's just everything that you've covered in this course up until tomorrow's lecture. We'll make a note on Piazza saying that also, but yeah, that is the fact. Other midterm questions? Okay, so the next thing, Contest 2, originally we were going to report the results for Contest 2 today. We know there were some issues with the contest server and the code online. Turned out what was happening was it was showing you visualizations using the old rules, even though you were being scored using the new rules. Because you haven't had a chance to see what your bots do when competing with other bots in the real way, we have extended the contest, so you now have until Saturday night to use the contest, resubmit versions of your contest bot. The server will stay up, we'll bring it down then, and we'll announce results of Contest 2 on Monday. So do people have any other contest questions? Okay, great. And then the last thing is that, as a reminder, you have a homework due tonight. So moving along, today's lecture is going to be on Markov models. Markov models are a special class of Bayes nets that turn up in a lot of practical applications. And so we're mostly going to be talking at a kind of high level about things that are special about inference in Markov models and special tricks you can use to do inference. And then on tomorrow we're going to introduce a slightly richer class, also just of special Bayes nets that are called hidden Markov models that have a little bit more structure. Before we get into the Markov models portion of this class, I wanted to do a brief recap of what we did last lecture on decision networks and VPI. So just to remind you, when we start looking at decision networks, is the slide incomprehensible? A little bit? It's a little dark. Yeah, so for those of you who are just coming in, something is wrong with the projector. ETS apparently is not going to come in time to fix it. So if you can't see something, just like yell or raise your hand, and I will draw it on the board. Would you like me to draw what's on the screen right now on the board? No. Okay, good. So as a reminder of how decision networks work, these look a lot like the graphical models that we've been working with so far, but they have two new kinds of nodes. We have what we call, let's bring up the pen here, we have what we call decision nodes that we draw with rectangular boundaries that look like this, and these correspond to choices you get to make in the world. And we have also utility nodes that we draw with diamonds that look like this, and these correspond to sort of utilities you are going to receive from interacting with the world. Think of them as kind of rewards you get for making the right decision. Slides are up for those of you who want to follow along at home. Okay, so we have two new kinds of nodes. We have choice nodes and we have utility nodes. And now we can ask new kinds of questions that we didn't ask in Bayes nets. In particular, we can ask questions about what decisions we should make in order to maximize the utility that we receive. So in order to specify one of these decision networks, we're going to use some pieces that look like the pieces that we had when we were doing Bayes nets inference, and that looks like this. This weather is some normal random variable of the kind that we've been looking at all class. and we're going to define this weather random variable in terms of a probability distribution table that looks like this. But we also have new things to specify for the other kinds of nodes. And in particular, utility nodes are going to be associated with tables that are structured in the same way as the nodes for the probability tables for variables, but rather than telling you the probability that some outcome occurs, they'll tell you the reward that you receive, the utility that you receive when that outcome happens. So here, for example, we have a case where it might rain or it might be sunny, and I'm trying to decide whether or not to bring my umbrella. And if I leave the umbrella at home and it turns out to be sunny, I really like that. I get a utility of 100. If I bring my umbrella and it rains, if basically I made the right decision about the rain, that's also good. I get a utility of 70. But if I make the wrong decision in either case, if I leave my umbrella and it turns out to rain, that's terrible. I get a score of 0. Or if I take my umbrella and it's sunny, that's also pretty bad because now I'm dragging around my umbrella while everybody else is playing ball off to the side. And so I get a reward of 20. And so the question that we're generally trying to ask when we work with decision networks is what is the action that I should take to maximize my expected utility? So if I don't know ahead of time what the weather is going to be, how do I decide whether or not to bring the umbrella with me? And so the way we're going to compute this expected utility is in the following way. It's kind of the obvious thing. It's just the expected value of the utility function under the uncertainty induced by all of the other random variables here. So we have here some P of W, which is the probability that the weather happens one way or another, and I'm just going to multiply that pointwise by the utility associated with all the events, and that's this, and this is how I get my expected utility. So we can compute this explicitly. Right here, I'm getting this 0.7 from the probability that it's sunny. When it's sunny and I leave my umbrella behind, I get this score of 100 again. And when it rains, which happens with 0.3 probability, I get 0 points because I don't like it when I leave my umbrella behind and it rains. So I add these two things together. This is basically a weighted average of all of my utilities under the probability distribution induced by my own choice and by this random variable W, and that's going to give me my expected utility for making this decision. We can do the same thing if we decide to take the umbrella rather than leave it, and we get a corresponding answer here. So the right thing to do, we see, right, if I leave the umbrella behind, my expected utility is 70. If I bring the umbrella with me, the expected utility is 35, so I want to leave the umbrella. Do people have questions about the kind of basics of decision networks and expected utility? Okay, cool. So what can we do with this? Well, the next thing that we can do with this is we can start to ask how much it's worth it for me to gather various kinds of information before I actually make my decision about what to do. So coming back to this weather domain again, maybe now we're not going to be able to observe today's weather ahead of time. What we will be able to observe instead is a forecast of what the weather is going to be. And so I want to know basically how much it's worth it for me to figure out what the forecast is going to be. And the way we can do this, so this quantity, how much it's worth it for me to figure out the forecast, is called the value of perfect information. Basically, the increase in utility that I get from knowing what the forecast is going to be. And the way we compute that is as follows. We first compute the maximum expected utility that it's possible for me to get if I don't know anything. That's what this null set symbol here means. And we saw on the previous slide that the maximum expected utility for this case is going to be 70. So you remember how we got that before. But let's suppose now we could actually observe the forecast. Well, there are two things that can happen, right? One thing that can happen is that the forecast turns out to be the bad forecast. And in this case, the maximum, knowing already that it's a bad forecast, the expected utility I can get, if I choose the best possible action, is going to be 53, right? So knowing that the forecast is bad changes my belief about what's going to happen today, changes my belief in particular about the distribution of W, and that's what's going to result in me kind of knowing that no matter what I do, the best expected utility I can hope for is the score of 53. Conversely, if the forecast turns out to be good, the opposite thing happens, right? So if I know the forecast is good, my maximum expected utility is going to increase in the following way, and expectation, if I make the right decision here, I'm going to get a score of 95 instead. Do people understand kind of where these things come from? Okay, so one thing that turns out to be confusing a lot once people stare at this a little bit more is, we're going to see in a minute that the expected utility, the value of perfect information is always positive. It is always good for me to know more. But I have this weird situation here where I found out that the weather was going to be bad, and suddenly I'm getting a score of 53. So how is it that this number has become lower than the expected utility if I didn't know anything at all? Think about that for, say, 60 seconds, and then we'll ask what people think. Talk to your neighbors. Yeah, so we're just doing a quick review from last class. Yeah. Okay, so where does this fit? Why is this 53 number lower? Yeah.
Because now we have to weigh it down because we are expecting the worst result to be more likely.
Uh-huh. And how do I reconcile that with the fact that the value of perfect information is always positive?
Because now the perfect information is suggesting that a bad result is more likely.
Okay, so the issue here is I guess it's useful to go back explicitly to the computation that we're doing here. Right, so the question is, where does this 53 number live in the expression for VPI that we have down at the bottom here? Yeah. It's one of the terms in the summation, right? So in particular, it lives inside the sum here, but it's only one of the terms. And so what the actual VPI is going to depend on is some kind of weighted average of these two things. And the sort of MEU that we get, kind of knowing nothing ahead of time, is this 70. This 70 is itself a weighted average of a bunch of terms. We looked at what those terms were on the previous slide. And we saw basically that, there you kind of make a decision ahead of time, and then you take the best, and you make the best decision that you can make before knowing what the outcomes are going to be. What we have here when we're computing VPI is the opposite case. So I get to observe some evidence, and then I'm going to make my decision. So yeah, I guess the reason people sometimes get tripped up is because you wind up with, at some point, in this VPI computation, a number that's lower, but the thing to remember is that it's just one term in the sum, and when we say that the value of perfect information is positive, we're saying that this whole sum taken together is going to be worth more than the sum that lives inside the MEU with only the original evidence. Yeah?
What if the forecast distribution is reversed, or like bad have a more weighted?
That's fine, right? Because if a bad forecast is more likely, then, I guess the way we have that set up, so what are the two ways in which a bad forecast could be more likely? It could either be that the weather is just likely to be worse, or it could be that the forecasters are really pessimistic and they make all the forecasts bad, right? If the bad forecast is more likely because the weather is just likely to be worse, that will also affect this number right here, right? On the other hand, if a bad forecast becomes more likely because the forecasters become more pessimistic, that will basically just flatten out this distribution that we have here and make it look more like this one. So we can we get less information out of the forecast, and so only these terms change, but in a way that doesn't change the value of perfect information. Yeah. In the back.
Would it be accurate to say that the VPI is like the expected increase in MEU?
Yeah. But, expected, where it's this kind of complicated tree-shaped process, right, where you're going to see what the value is that you're trying to measure, and then you're going to make your decision. So it's a complicated expectation to compute. Okay, so just to wrap this up pretty quickly, since you guys do seem to remember all this well, the main things that you should keep in your head, the properties that VPI has, it's non-negative, and we just saw why that is. It's non-additive, which is to say that the VPI of seeing some node and then the VPI of seeing some other node, if I get to see them both at the same time, that might be more than the sum of their individual VPIs, it might be less than the sum of their individual VPIs, or it might turn out to be exactly the same. And the last thing is that it doesn't matter what order I make all of my observations in. All I care about is all of the evidence that I'm going to have in my hand at the end of the day. So that's basically all I wanted to do to wrap up the VPI review. Do people have questions about this material before we move on? Yeah?
So if order was independent, what if you observed a node that gave that made like a path active, and then the next observation was on like the other side of the path? Wouldn't that be order?
Sure. I guess the point is that, at the point at which you make your decision is the point at which you've observed all of the evidence that you're eventually going to observe. Right? So sort of the order in which I choose to pull these things out of the Bayes net doesn't actually matter, because at the end of the day, I'm conditioning on all the available evidence, and that's what I'm using to do this computation. Other questions? Okay, cool. So let's skip over this and get to the real subject of today's lecture, which is Markov models. So what are these things? When we see real-world modeling problems, they often have a particular kind of structure, which is a sequence structure, right? So when I'm trying to do speech recognition, what I get to observe is a sequence of sounds that somebody is producing, and I'm trying to infer from that a sequence of words that cause those sounds to appear. When I'm trying to figure out where a robot is located, what I get to observe is a sequence of measurements from the sensors of the robot, and I'm trying to make a final decision basically about the sequence of positions that the robot was actually located on the basis of these sensors. And there are a bunch of other examples that come up with this, right? If I want to predict the stock market, it's useful for me to know what the stock market is doing today and how what it's doing today relates to what it's doing tomorrow, and so on and so forth. And so it's very, very common to have graphical models, to have Bayes nets that have this kind of sequence structure or backbone structure that look like this, where I have a bunch of observations, and they're just chained together in a sequence that looks like this. To make this somewhat concrete, let's go back to this Ghostbusters demo that you guys have been looking at in the class several times already. Let's bring this up. This is Ghostbusters. Like this. Okay. So can people see this? Can people read the numbers? No. Can people see what color the numbers are, at least? Okay, that is probably going to be enough. Right, so remember how this works. I get to choose squares on the grid. I will observe some noisy reading of the distance to the ghost on the grid, and that's what's going to tell me information about where the ghost is located. Where should I? Okay, do people see that we're kind of getting warmer around here? Oh, God, this is terrible. Okay, the ghost is probably in this square, right? Can people see the square that is being pointed at? Okay, so what we've been looking at so far is we have a single position of the ghost, and it's generating a bunch of different observations that I have. What if it were now the case that the ghost was not just sitting still waiting to be found, but could actually move? So what I've computed now is some distribution over where I think the ghost is at this moment. Let's elapse time. The ghost can start to walk. And what we're going to be looking at today are models for basically, even if I don't get to make any observations after the initial time step, figuring out where the ghost is likely to be after some number of time steps. So here we have a model where the ghost is basically going to try to move in a circle around the board, and we want to be able to predict after 10 time steps where is the ghost. So let's start making some observations again and seeing how good this prediction was. We think it's here. Oh, it's not actually there. We think it's here. It's not actually there. Well, okay, so it's moved a little bit clockwise, kind of in the way that we were predicting, I think, hopefully. Yes, for sure. Okay, right? So if we press bust now, Oh. Okay. Inference goes wrong sometimes. But in general, what we're going to be looking at in class today are ways of doing this as best we can with all of the available evidence. I want to do one more thing, and I was going to use Davis, but Davis has left, so I will need a live volunteer. All right. Okay, so blindfold yourself. Actually, don't blindfold yourself yet. Stand right here, and then blindfold yourself. Okay, if he takes 3 steps, how many of you think he will have passed the coffee mug? Show of hands. Okay. What if he takes 4 steps? How many of you think he will have passed it? Okay. Pretty much everyone in the class thinks after 4 steps. What about after 8 steps? After 8 steps, do you think he will have passed the bag? Okay, slightly fewer of you think that after 8 steps he will have passed the bag, even though basically the distance between him and the cup and the distance from the cup to the bag are about the same. Let's see what actually happens. Take 4 steps. Please don't fall over or I will get sued. Okay, so he's being cheeky, and he's made it all the way to the bag after 4 steps. So those of you who said yes, you're right. You can take it off now. Thank you very much. Actually, I want to do one more thing. Stand where the cup is. Stand where you were at the very end. Okay, put it back on. If he's trying to figure out where he is, and he's just having reached the bag, taken the thing off, or reached out to the side and felt the bag there, does it matter what he saw before he put the blindfold on? Who says yes? Some people say yes. Who says no? Who didn't raise their hand? Lots of people didn't raise their hand. Okay, so, I mean, this seems like a kind of common sense thing, right? If I get to open my eyes, and I know I'm standing right here, and I'm trying to figure out where I am, this position tells me everything that I need to know. And how I got here doesn't make any difference at all, right? The kind of observing where I am after taking T steps, I don't care what happened in the past at all, because I know exactly where. If you take one more step, right, you should now be very confident about where you are. Having opened your eyes after 8 steps, put the blindfold back on, and taken one more step, than you would have been if you started out and just walked the 9 steps. So that's all. You can take the blindfold off. Thank you very much. What I want you guys to keep in your heads as we're going through the lecture today is just this image of somebody walking forward with a blindfold on and very occasionally opening their eyes, because that's essentially what a Markov model is. So let's formalize this a little bit. Like we said before, we're going to be looking at a class of graphical models that look like this, that are just chains. But this is going to be a special class of graphical models because they're only going to be described in terms of 2 probability distributions. Right before, when I saw a model that looked like this, this is what I want. When I saw a model that looked like this, how many distributions did I need to specify a chain of length 4? Somebody shout it out. I have 4 random variables, 4 distributions, right? In a Bayes net, every random variable gets its own probability distribution. When we talk about Markov models, generally what we mean are what we call stationary Markov models that have the property that the transitions are the same across all time steps. So the only thing I need to know is what is my prior distribution over where I'm going to be at time t equals 1, and then for any time step, what's the probability of going from some state at that time step to some other state at time t plus 1. Does this look familiar? This should look familiar because it's basically the same way MDPs work, right? MDPs also have this property that the transition function is unchanging over time. It depends on kind of what action I take and also the current state I'm in, but not how long I've been playing the game for. So you can kind of think of a Markov model as what happens when you're watching somebody else play an MDP, right? Where you just get to see states evolve over time, and that distribution is unchanging. People clear on the basic setup so far? Okay, good. So we should be able to breeze through this, right? What are the independence assumptions that we're making here? Well, if I want to write down, why did this crash? Because it's trying to reinstall Java, which is not what I want right now. Where did Keynote go? Okay, no Java updates today. So if I want to know what the joint distribution induced by a Markov model is, we can write it out using the chain rule and then introducing the independence assumptions that this particular BaseNet allows us to make. And if I'm running for t time steps, the probability of this whole sequence of observations that I get, if I want to know the joint distribution of the whole sequence, is just this initial distribution times the transition distribution once for each time step up to some fixed time t that we're caring about. So in particular, we know kind of the independence assumptions that we get to make in a Markov model that looks like this. If I observe nothing, is this first state x1 dependent on this final state x4? Hands for yes? Hands for no? Okay, if I don't get to observe anything at all, remember, deseparation. This is an active set of 3. This is an active set of 3. So unconditionally, these two things do depend on each other. Let's use a different color. These two things do depend on each other. What happens if I observe any chain in any node in the chain? Now are they dependent on each other? Hands for yes? Hands for no? Okay, everyone's saying no because, in fact, by making this observation here, this is no longer an active triple. So if this doesn't look familiar, just go back and review your deseparation notes. It turns out the answer to these kinds of independence queries in BaseNets, or in Markov models in particular, are really simple. It's just that if I have a node at time t and a node at time n, if I observe anything in between them, then they are independent, and otherwise they are dependent. And in particular, if I want to know sort of what's the probability of x little n given xj and xi and xk like this, the only thing that xn is actually going to depend on is whatever of these is most recent. So if k is my last observation, it'll just depend on k. Is it clear to people why that is? Okay, this just falls out of the deseparation stuff that we've been doing before. So coming back to the example of walking across the room, right? Once I've observed my position when I'm standing here, it no longer matters what other observations I made when I was standing previously in places in the room. So one of the things that comes up when people talk about Markov chains is we often treat them as though they're just infinitely long sequences of things. You haven't seen infinitely large graphical models before, but basically, I'm always going to be doing inference up to some fixed time step, and you just treat it as a model of fixed size up to that time step. Questions? Okay, cool. So let's look at an example of this to make this a little bit concrete. Here I have a Markov chain in which these variables x can take on 2 values. It can either be rainy or it can be sunny. And initially I know, say on Monday, that it's for sure going to be sunny outside. So what do I need to specify this distribution other than knowing that it's going to be sunny on Monday? Well, I need this transition matrix, right? And this transition matrix is just a normal conditional probability table of the kind that we've been looking at so far. It looks like this, and noticing in particular that it sums up to 1 over values of x at time t minus 1. When we are dealing with hidden Markov, or with Markov models in particular, you will occasionally see these things written in a couple of slightly different ways. You will either see them with these kind of finite state diagrams that look like this, or these kind of block diagrams that just show forward transitions. This is not a graphical model. Let me say that again. This is not a graphical model. This is not a BaseNet. This confused the hell out of me when I was learning this material to begin with, because it looks very much like a graphical model. It is not, right? This is just a different way of representing this conditional probability table that happens to get used, I think, mostly for historical reasons when we're talking about Markov models in particular. How do we know this thing is not a BaseNet? Yeah, in the back. It has cycles, right? And even worse, it has self loops. So yeah, this is not always going to be true that these things will have cycles, that they will have self loops. But pay attention to context and be aware that this thing is not a basenet. So that's the representation. Again, hopefully this looks familiar. And now we can start to ask the normal kinds of inference questions that we ask. So if I know initially that it's going to be sunny, what's the probability distribution over times after one step? Well, we just use the rules we know, right? We know that sort of the probability that of x2 is equal to the sum over values of x1, probability of x1, probability of x2 given x1, right? What am I doing here? I'm summing out. I'm running variable elimination on the first step of a chain that looks like this. So I've first joined x2 and x1, that's this multiplication step here, and then I've eliminated x1. And what I'm left with here is the probability, in this case, that x2 is equal to sun, or more generally, a distribution over probability values for x2. So that's how I get from time t equals 1 to time t equals 2. How am I going to get from time t equals 2 to time t equals n? Hand, somebody? Think about it for 30 seconds, and then we'll come back. Talk to your neighbors. All right. Somebody, what do we think? Please, yes, in the back.
So you just calculated probability of x equals sun right there, right?
Yeah.
So you could use that information to calculate like p of x3 equals sun, for example, in the same manner, and then you could just keep on chaining that until you get to the next step.
Exactly. So the thing that we observe here is that we were able to get from probability at x1 basically to probability of x2 marginally, right? That I can compute this thing just using kind of one step of variable elimination. And now what I have is p of x2. Well, this thing is the same shape as p of x1, right? So the thing that I did to get from p of x1 to p of x2, I can just do over again to get from p of x2 to p of x3. And I can do it again and again and again until I get to whatever time step I'm doing inference over. And in particular, if we draw our Markov chain here again, this is just what happens when we run variable elimination repeatedly, right? I join these two things together, then I eliminate this one. I join these two things together, then I eliminate this one. I join these two things together, then I eliminate this one, and eventually what I've come up with is a probability distribution just over some particular value in the chain. Does this surprise people? Yeah.
For Markov models, when we only care about the day before, if we were going to looking very far ahead, and it's going to infinity, would the probability distribution approach just 1?
That is an awesome question. I don't know what you mean by probability distribution approaching 1, but it will usually approach something, and we're going to be talking a lot about that today. In fact, I think that's what we're talking about just now. So yeah, to kind of erase all of the chicken scratchings on the slide here, right, this is just writing out explicitly what we were doing before. If I want to know the probability at some time t, I can get that from the joint probability of being at time t and the previous time step, and I can get that from just multiplying together whatever I had calculated before. Yeah?
Can we extend this model a little bit? Now, for example, we have px xt, and now px just depends on pt minus 1. Can depends on pxt minus 1 and pxt minus 2 as well.
Yes. So what that looks like is a model like this to kind of draw this explicitly, where we have, sorry, not that, like this, and so on. This is what's called a second-order Markov model rather than a first-order Markov model, because things depend not only on the current time step, but also on the time step one back. It turns out that when we actually implement these things in practice, and this comes up all the time, in speech recognition, for example, if I want to know what the next sound to come out of your mouth is going to be, it's useful for me to know the last 4 or 5 sounds that came out of your mouth. You can transform this into an ordinary Markov model that looks like this, just by changing the state representation a little bit, so that your states now kind of remember all of the history. And it's a little beyond the scope of this class, but I encourage you to think about how that might work when you all go home. And if you're interested in these kinds of things, take CS 288 when it is offered in the spring, because you'll be doing a lot of higher order Markov models. Other questions about this? So this thing that we've written down here, which again is just variable elimination, is sometimes referred to as the forward algorithm. We've called it the mini forward algorithm here because you're going to be seeing a slightly more complicated version of it next class for hidden Markov models rather than regular Markov models. So we call this the mini forward algorithm because nothing is hidden. Okay, so let's come back to this question of what happens if we run our Markov chain forever. So in particular, this weather example that we have here, if it's initially sunny, this is what my distribution over values of the weather looks like at time t equals 1. At time t equals 2, it looks like this. We saw how to do that on the previous slide. We repeat that process again, basically forgetting that this happened and starting over. And like we said, we can keep doing this forever. And we will find after sufficiently many time steps that this gets arbitrarily close to 3/4, 1/4 for whether it's sunny or rainy. Okay, so that's what happened if we started out when it was initially sunny. What if it's initially rainy? Well, now at time t equals 1, we have something that looks like this. Raise your hand if you think that after infinity time steps, this is going to converge to any value. It's going to converge to something. Okay, everyone thinks it's going to converge to something. Who thinks it's going to converge to the same value? About half. Who thinks it's going to converge to a different value? Slightly less than half. Okay, let's run this forward. Sure enough, it converged to exactly the same value. In particular, for this hidden this Markov model that we have here, any starting configuration that we initialize from, after sufficiently many time steps, we're always going to converge to something that looks like this distribution over the states. So, to say that more formally, if I start from p and 1 minus p for arbitrary choices of p and 1 minus p, we're going to wind up here. Let's look at some concrete examples of that happening back in Pac-Man land again. So let's, in particular, look at this kind of circular example we were looking at before. Okay, so I'm going to make a bunch of initial observations so that I'm pretty sure where the ghost is. Okay, we're pretty sure the ghost is right there, yeah? As I elapse time, what's going to happen? Well, I have some kind of transition model of how the ghost is moving, but it's not a perfect transition model, right? I don't know exactly what square it's going to go to next. I just have a kind of general sense of the area of the board that it's going to wind up in. So over time, if I don't make any more observations, you can see right here that this value, the sort of highest value, the highest probability that any square gets assigned for being where the ghost is located is going to attenuate over time. So the longer I run this for, the less and less confident I get about the ghost position. And if I just keep mashing this button, eventually I'm going to wind up with something that looks like the uniform distribution here, where I'm totally unconfident, like I was at the very beginning of this game, about where the ghost is. This is not the only way these things can fall out. So here's an example of another version of this board where I want this one, where I'm going to start by making a bunch of observations of the ghost's position initially. Oh, come on. Okay, so it's there, right? We're pretty sure it's there. Where did it go? This is terrible. Okay, we're pretty sure it's there now. As I elapse time, this is a model of the world in which the ghost likes to sort of gravitate towards the center of the board. And so the longer I wait, I no longer wind up with a probability distribution that's kind of smeared out over all of the positions on the board. Instead, I wind up basically thinking it's 50% going to be in one of the middle squares and 50% going to be in one of the other middle squares. What's amazing about this particular set of dynamics is that even if I don't know anything about the ghost's initial position, and all I know is that the ghost tends to gravitate toward the center of the board, without making any observations at all, after letting enough time elapse, I'm going to become pretty confident that the ghost is located in the center of the board. Can people see that? Both like literally, can you see it on the screen? And also, does it make sense why you can set up transition dynamics that have this property? Okay, great. So, that is not what I wanted to do. Yeah, so we looked at this before. We looked at some examples. So what this is called, when after we let lots and lots and lots of time elapse, we eventually wind up with kind of a fixed distribution, this is called the stationary distribution of the Markov chain. What that stationary distribution is obviously going to depend on the parameters of the Markov chain itself. So for a lot of chains, the influence of the initial distribution gets less and less and less over time. So where I started out at time t equals 0 is going to matter less as things go forward. And the further I am in the future, the less I care about observations I've seen in the past. And the sort of extreme version of that is that after arbitrarily long, I don't care where I started from. This is called the stationary distribution. We write it like this, p sub infinity, which we've kind of cheekily here written with the following recurrence relation. If this is the stationary distribution, if this is where we end up after infinitely many time steps, then after infinitely many time steps plus 1, we expect that distribution to be the same, right? So these two things are equivalent. But I can also write that using this same variable elimination rule that we used for doing forward inference at all of the previous time steps. So, at time infinity plus 1, this is the probability of transitioning, for each state, the probability of transitioning into that state from wherever we were at the previous time step. So this is how we're defining the stationary distribution, and this is a property that comes out of being a Markov model. Do people see both of those things? Question? Great question. Remember it. We'll come back to that. So, if there is a stationary distribution, let's actually back up here. If there is a stationary distribution, it will satisfy this relation right here. We can use this fact to compute the stationary distribution for a Markov chain without having to actually do the forward simulation for all time. So coming back to the sun and rain example we had before, we can just write things down like this, right? If p infinity of sun is the probability of being in the sun state in the stationary distribution, then it will also be the case that that's the probability of transitioning from sun while in the stationary distribution, plus the probability of coming into sun from rain while in the stationary distribution. So we can say that, and we can say the same thing for rain. So if I have these two equations, what can I do to compute the stationary distribution? Think back to your high school algebra class. It's a system of equations, right? Two variables and two unknowns. So we can do this. We get the following equation here. This is just plugging in values of these things from the table over here. We get two more equations that look like this. And if we do some substituting, we wind up with something that looks like this. So the probability under the stationary distribution of being in the sun is 3 times the probability of being in a rainy state. Probability of being in a rainy state is 1/3 of the probability of being in a sunny state. Have we actually solved this problem? No, right? What went wrong here? We had two equations, we had two unknowns. Right. So in particular, kind of if I know the probability of being in the sun, I already know the probability of the rain. That's fully specified by sort of being a probability distribution. And the one thing that we haven't encoded here is the fact that these things do actually have to correspond to probability distributions. So in particular, the probability of being in a sunny state and the probability of being in a rainy state have to add up to 1. So this is another equation that we can introduce. It's not dependent on the first. And finally, I can put these two things together, this statement here and this statement here. And that gets me my stationary distribution for this Markov chain, which, as we saw on the previous slide, by simulating forward a lot, is 3/4 of the time in sun and 1/4 of the time in rain. So what does this mean? This means that if I ask you arbitrarily far in the future, what's the weather going to be? You should say, well, it's going to be sunny with 3/4 probability, and it's going to be rainy with 1/4 probability, right? This doesn't mean that in the future we're in some kind of weird superposition of states where it's partly rainy, it's partly sunny. This is just the probability distribution that at any time step arbitrarily far away we think we're going to have. People happy with this? Okay, here's an example of another stationary distribution. Yeah, before we go on.
Can you explain why the first two equations were nearly independent?
Sorry. Yeah, I mean, so there are two ways of coming at this. You can either kind of just like, right, these are going to be, probability of rain is going to be a scaled version of this, right? Because every coefficient that I have here is here, let's erase all of the clutter. I cannot erase all of the clutter. Every coefficient that I'm going to have in the second equation is 1 minus the corresponding coefficient. So this whole thing is just 1 minus this thing. If you want to think about it in kind of information theoretic terms, in fact, to specify this table here, I only need 2 numbers, right? I need the 0.9, I need the 0.3, and everything else falls out of the fact that these things have to sum to 1. So if I have 3 states in my Markov model, it's enough to sort of do this computation for 2 equations, and then the sum to 1. Okay, so what I would like you all to do now is figure out the stationary distribution for the Markov model that we have on the screen, which hopefully everyone can see. Can everyone see that? Can anyone not see that? Okay, great. You have 5 minutes. Just not a good time. So if you can't see the screen, that's actually probably behind the podium for everyone who's sitting on this side of the room, so that is equally unhelpful. Yeah.
So when we had these two dependent equations, you did need to write both of them down, right? Because when we had together.
Right. So, you know, in fact, one of your equations is going to come from kind of the definition of the stationary distribution, and one of them is going to come from the fact that what you get out at the end has to be a probability distribution. So it sums to 1. Yeah.
What if you had more than one? Like, what if it was not binary?
Like if you had 3 hidden states, then you would have more equations. And at that point, right, kind of only the last of these transition probabilities is linearly dependent on all the ones that come before it. Yeah. Yeah.
Why doesn't independent distribution converge to the sum of or I was thinking intuitively the probability that it will be as x to the A will be either you got from A to A or from A to B. So why wouldn't it be the case that P of B A would be P of A given A times P of A plus P of A given B times P of B?
I mean, that's what it is, but it's not. Here, we go back. Right. New color. This thing here is what you just said, right? But in particular, this is something you can't read off of the table, which is why you wind up with this system of equations rather than just being able to multiply things out directly. Raise your hand if you want more time. Nobody wants more time. Okay, great. So skipping through all of this. That's getting ahead of ourselves. Okay, so how am I going to do this? Somebody shout out one system, one equation that I can use here. Sorry, you can't see the thing anymore. Somebody on this side of the room. Give me one equation. Yeah, in the front.
PB equals PB given B times PB. That should be.
Yeah.
And plus.
I guess. Sorry.
PB given A times PB.
Okay. And in numbers, what is this?
Should be 1 over 3 times PB plus 1 over 2 times PA.
Okay. What's my other equation?
P infinity B equals 1 minus P.
Yeah. So what do I get if I put these two things together? Somebody else? Someone from this side of the room? Somebody, please. Do you agree with this so far? Okay, good. Yeah, in the back.
I got PB equals 3/7 and probably given equals 4/7.
Does everyone else agree with this? Okay, good. I didn't actually do this before time, but okay, excellent. So you all know how to calculate a stationary distribution from a Markov chain. There was a question before, which is it the case that all Markov chains have stationary distributions? The answer is no. And what I would like you to do for the next 5 minutes is try to construct a Markov chain that has no stationary distribution. And what that means basically is a Markov chain for which you can't satisfy, you can't come up with a well-formed solution to this, or equivalently a Markov chain such that no matter where you are, you will wind up in a different state at the next time step. From any state that you can actually reach under the Markov chain, you'll wind up in a different state at the next time step. Talk to your neighbors. This is a, yeah. There was a question.
I was going to answer, but I'll wait.
Okay, yeah. Give everyone a chance to think about it. Okay, does anyone want more time? Okay. Okay, let's bring it back. Who has an example of a Markov chain without a stationary distribution? Yeah.
So if you have like 3 nodes, A, B, and C, and the transition probability from B to A and from B to C equals like 1/2.
Okay.
Or from B to A and from B to C, not from C. Yeah. And then self loops from A to C with probability 1.
Uh-huh.
So, like, there's a probability that you'll get stuck at either state A or at state C for like the rest of the time.
Uh-huh.
So, therefore, there isn't just like one stationary distribution.
Okay, good. Yeah, so the key thing to notice here is when we say, does it have no stationary distribution, in fact, this is a slightly more complicated statement. It's a statement about both the transition function of the Markov chain and also the initial distribution. So if I initialize this Markov chain such that probability at time 1 of being an A is equal to 1 and 0 everywhere else, the final state that this Markov chain winds up in will have probability of A being 1 and 0 everywhere else, right? If I started off in state B, it will stay in B forever. If I started off in state C, then it will wind up in A with probability 1/2 and B with probability 1/2. And, I've done this the wrong way. Thank you. Let's just scratch that out. This is C, and this is B. If this is the case, then I'll wind up in each of these things with probability 1/2. Or if I start with a uniform distribution of all of my states, then I'll wind up kind of attracted to the same stationary distribution over here. Did anyone else have a fundamentally different kind of Markov chain? Yeah?
If you from A and you will just go to B, and if you from B you will just go to A.
Okay, good. Yeah. So this, let's erase everything here. Well, we can save this. So here we have a Markov chain that looks like this. When I'm in A with probability 1, I go to B. When I'm in B with probability 1, I go to A. If I start in state A with probability 1, where am I going to be after arbitrarily many time steps? I don't know, right? Suddenly it actually depends basically on whether it's an even numbered amount of time or an odd numbered amount of time. So there will not be a convergence when we do this update operation. What happens if I start in A with 50% probability and B with 50% probability? Then we actually will have a stationary distribution, right? Because I start, kind of 50% on A, 50% on B. After one step elapses, then, the one that was in A is now certainly in B. The mass that was in B is now certainly in A. And so we have reached, in a kind of weird way, a stationary distribution of this Markov chain. So that will converge. In fact, it will converge immediately. But there are starting distributions that will never converge. And in fact, every starting distribution but the one that's evenly split between those two will never converge. So these are basically the kinds of behaviors you see that will cause there not to be a unique stationary distribution for your Markov model. You can either have it be the case that you get this kind of oscillating behavior between multiple states, or you will have it be the case that you can get stuck in kind of sync states from which it is impossible to return to other parts of the Markov chain. And so this is a huge area of study in probability theory and statistics, and if you're interested in these kinds of things, there's lots of stuff in other departments that's, entire classes, entire PhD dissertations are written just on analyzing Markov chains. But these are kind of the categories of behavior to have in your head. Question?
What if the chain had obsolete observed variables such that there could be no stationary distribution?
What do you mean by obsolete?
Just historical variables, not recent, not prior node, time node.
Okay, so I guess the question is, how does this notion of stationarity interact with being able to make observations in general? Yeah, so when we ask about the stationary distribution of a Markov chain, we generally mean assuming that we are never going to observe anything other than the initial distribution. if you do get to make observations, then the kind of long-term behavior of the Markov chain is going to depend, as we saw before, only on the last observation that you made.
What about the prior distribution in the chain?
Yeah, so that's, I mean, this is the whole point, right? That if I know something about the distribution here, and then I observe this variable, then everything that happens in the future is conditionally independent of everything that happened in the past, including my starting distribution. So, you know, for practical purposes, if you're asking about the long-term behavior of this chain, you can think of it as just starting here and forgetting everything that happened before then, because the past doesn't depend on, the future doesn't depend on the past beyond whatever your most recent observation is.
What happened in nodes when you had like a t minus 3 node variable, you didn't have your t minus 1, your last observed variable in the chain?
So, question is, I have something like this, and I want to know what's happening here. Yeah, so, you know, this is the sort of normal inference procedure we saw before. You can basically chop your chain off here because you know what state you're in at this time, and then, you know, you do variable elimination to figure out what the distribution is at this node, and then you do it again to figure out what the distribution is at this node. And that's just that forward update that we had on previous slides. Other stationary distribution questions? Okay, so the fact that Markov chains have stationary distributions and that in general we can compute them turns out to be itself a really useful fact for a lot of applications. Who here, raise your hand if you have heard of PageRank before? Okay, most but not everyone. So back in the bad old days, when search engines were things that you sort of paid them some amount of money and then they would list you when certain words were searched for. The Google people came along and said, no, there's a better way of doing this. We should just be computing based on the link structure of the internet rather than people who are giving us money, which are the good pages and which are the bad pages. And so in particular, you can think of the whole internet as a kind of graph, not a Markov, not a Bayes net, this graph that we're drawing. This is the internet, pages link to each other, and maybe we want to treat all links as the same, and I have some kind of complicated link structure. And what I want to know is if I start on some random page on the internet, and I click a random link on that page, where am I, and I keep doing this procedure, choose a random link, choose a random link, choose a random link forever, where am I going to wind up? And assuming the internet has kind of a non-pathological link structure baked into it, there's some stationary distribution over all of the web pages on the internet induced by this random linking process that we've talked about, right? Just using kind of the machinery that we've talked about on the previous slide. So you can ask, of the whole internet, if I start from a random place and I start clicking randomly, where do I wind up? And you kind of expect that sites that are linked to a lot by other sites that themselves tend to be influential, will be the sites where you tend to end up, but you want to make this kind of immune to gaming. So I don't want it to be the case that I can just make a million websites that nobody else ever links to, all of which link to the one website that I want to drive a lot of traffic to. And in a model like this, what happens is that links out of influential sites count more than links from sites that it's impossible to reach, right? Because if I'm really likely to be at a site A and A links to B, then I'm probably really likely to be at B too, much more than if I have to start over here from something that nobody is linked to. So this was the kind of core algorithmic thing that made Google work originally. It turns out now everyone does this. This is not so much of a useful signal anymore, and real search engines use a lot of information and not just this kind of ranking signal. But this notion of computing the stationary distribution of a random walk through the internet was basically what took us from a world in which search engines don't work to a world in which search engines do work. So this is one kind of natural application of computing stationary distributions of Markov chains. Notice star on this slide. So this and the thing that we're going to talk about next are cultural enrichment, and not something you'll be tested on. But the last thing that I wanted to bring up here, sorry, we don't care about that, is to actually tie this notion of figuring out distributions and stationary distributions of Markov chains to something that you saw in an earlier portion of this course, which is simulated annealing. Remember how simulated annealing works. I have some kind of energy landscape here, which basically tells me how good a configuration I'm looking at is. And it allows me to jump, if I'm at some point here, it allows me to jump to other points on this graph. And I like to jump downhill, and I like to jump uphill slightly less. So let's choose a different point. If I'm sitting here, with some high probability, I want to go down the hill. With some low probability, I want to go up the hill. And I'm going to run this procedure forever, or I'm going to run this procedure for some fixed amount of time. This is a Markov chain, right? Every state that I'm in, every sort of configuration that I've assigned to the variables in my problem corresponds to some state of this chain. And when I do this jumping operation, that's just a transition model for my Markov chain, which will take me somewhere else. And so we can reasonably ask, if I run simulated annealing, or sort of annealing without changing the temperature for long enough, what is the stationary distribution? And so in particular, the way you sort of prove formally that these techniques work is you show that that stationary distribution is going to place some kind of probability on the best solution to your problem. And if that turns out to be true, then kind of eventually you will visit the best solution to your problem. And this is a well-formed inference procedure. So, again, kind of major area of active research still, but kind of cool in that we can use these sort of probabilistic analysis techniques that we've been developing right now to reason about other inference procedures that we develop, which I think is something really cool. So that's it for Markov chains generally. And just as a preview for next class, we've been assuming so far that basically the things that I am observing are the states that I care about themselves, right? So as I'm taking my kind of like lurching walk across the room, once in a while I get to open my eyes, I know exactly where I am, and now I don't care about the past at all. What we're going to be seeing in hidden Markov models is something where the true sort of underlying state you care about, you don't actually get to observe. And what you see instead are noisy signals that are correlated with the state that you're really in. And what we're going to try to do is figure out what state we're actually in based only on these noisy observations that we get. And that's called a hidden Markov model because the Markov part of it is hidden from us. So, see you tomorrow.
Thank you.